You are listening to EE Times On Air, and this is EE Times Current. I'm Eric Singer. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, we hear from Dr. Dylan Muir, who's in charge of research at SynSense. Your hosts are Dr. Sunny Bains of University College London and Dr. Giulia D'Angelo of the Czech Technical University in Prague.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny will be talking to Dr. Dylan Muir of SynSense about the challenge of commercializing neuromorphic technology. After the interview, we will be talking to Ralph Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. Dylan has been rising through the ranks at SynSense since 2018 and is now VP of Global Research Operations and Program Manager for the company. SynSense has been putting out various products over the last few years, and as you'll hear, a new acquisition means that the company will have even more scope to integrate for low-power vision processing. There are links to his work and some of the specific papers we'll be discussing on our website. You can check them out at brainsandmachines.net. I met Dylan at SynSense's Zurich office. Dylan Muir, welcome to Brains and Machines. I want to start by asking you about your technical background and how you got into this field.
Thanks, Sunny. It's really nice to talk with you. My background is mostly technical, engineering, computer science. I studied in Australia. I was always interested in intelligence, human intelligence, and neural networks. I joined some research groups for neural networks during undergrad, but I realized that I needed to understand how human brains worked if I needed to really understand intelligence. And that led me to Switzerland and a computational neuroscience PhD. I deviated slightly away from my engineering roots in a more computational direction, working in experimental neuroscience groups with building computational models of the brain. And after a stint in academia, I've moved back now in a slightly more engineering direction. So taking that understanding about information processing in neural networks and putting this to work commercially.
So tell me about SynSense and how you got involved with it and what your day-to-day involves here.
SynSense was founded by Giacomo Indiveri and Ning Chao, both of whom were at University of Zurich in ETH Zurich. I actually started my PhD with Giacomo a very long time ago and then moved a little bit away from the very engineering roots. So I've known Giacomo and I've known his research and his hardware, his technology for a very long time. And just as I was coming out of a postdoc, they decided to try and commercialize the neuromorphic architectures that Giacomo and his group and Ning and his colleagues have been designing for a long time. At that point, I felt that this was a good time to work on commercialization of that hardware. The hardware always struck me as very cool. And at that point in 2018, I felt like I knew what to do with it commercially. I thought we could bring it to something which could be a product that people could use.
So you have two main products, as I understand it, Xylo and Speck. Can you tell me a little bit about each of those?
Sure. Let's start with Speck. Speck is a vision processing platform, fully integrated. We have a small vision sensor coupled with our neuromorphic processing cores on a single chip. It's designed to be a low-cost, low-power edge vision platform. And it just so happens to be based around neuromorphic concepts. So we have a DVS, an event-based vision sensor, plus some spiking convolutional neural network cores on Speck, designed to work directly with the DVS sensor in a fully asynchronous digital way. And we can build and deploy vision processing applications to this chip for a few milliwatts of power consumption. So that's the Speck product. That's obviously designed for edge applications, smartphones, IoT, smart home devices, anything where a little bit of vision-based intelligence is a good fit. It's designed to be a smart sensor. We're not producing a beautiful image. It's a machine vision sensor, which gives you a smart output, which could be a gesture. It could be detection of presence or something along those lines.
So before you move on to talk about Xylo, why don't you give me an example of a specific application that's been run on this chip?
A smart presence detection is a good application there. We're working with a group for sensitive detection of door entry and exit intent, something which might be currently done with a very cheap PIR sensor is not very selective. So we can't distinguish between someone walking past the door versus walking away with a PIR sensor. We can't distinguish between a child and a large dog, for example, because we are basing our vision applications around convolutional neural networks. We can distinguish not only between a human and an animal, we can distinguish between a human walking beside the door versus walking towards the door, or walking towards versus walking away from the door. So we can deploy applications which are very, very selective in this visual input way. Another good example is a vision-based gesture detection module, right? So we can build a 14-class vision-based gesture detection sensor and provide this to an OEM, a manufacturer, and they can use this in a smart home device to provide gesture recognition and detection for a consumer device.
Okay, so let's move on to Xylo.
Xylo is a family of devices for natural signal processing. This means things like audio processing, audio input, vibration monitoring, accelerometer, IMU-based motion input for human movement, for example, or animal movement. These sorts of signals which are low dimensionality but have a very important temporal extent. So it's a slightly different spiky neural network architecture. It's again a fully digital device, but with a slightly more complex neuron model designed for temporal signal processing.
I want to ask you more about the design choices in the two, but just sticking with applications for Xylo before we move on, what would be some good examples of those?
Mm-hmm. For Xylo, our first hardware is designed for audio applications, combines a spiky neural network core for inference with a very efficient audio interface. And so we're deploying things such as keyword spotting, acoustic environment detection and analysis, applications like this. We've also prototyped and fabricated an IMU-based motion front-end interface for motion sensing. There we're looking at applications such as human movement classification, which could be for a smart consumer health device or smartwatch. We're looking at animal motion and movement as well for maybe consumer animal health analysis, applications like this. We've also examined vibration-based applications, for example, predictive maintenance detection for industrial applications. These are all examples.
That's great. You mentioned that both of them are using digital technology. Can you talk about the different kinds of design choices that you had to make in order to get these products right and to get them at the right price point? And so analog versus digital, synchronous versus asynchronous. Maybe let's start with inference versus learning. So both of these are inference-only chips. Can you explain why you decided to go that route?
That's correct. All of our hardware is inference only. And the reason for that is really a commercial one. On-chip learning is very expensive in terms of silicon area required, especially gradient-based learning, which is what we're mostly using for building applications in 2023. Training an application from scratch on chip is very difficult in terms of managing access to data, getting a good outcome of the learning process. So on-chip learning becomes something which is difficult to accomplish well in terms of an application, something which is very expensive in terms of silicon area and therefore power and also cost. And for most commercial applications, any sort of reconfiguration or fine-tuning is likely something which is done either only once and then never again, or done for very short periods and then the application is frozen. And if that is the case, the training, learning, reconfiguration part is something which can be taken care of by an application processor in a consumer device and off-sourced from our silicon. And that means we can keep the costs and energy consumption of our chips minimal.
So that's the inference side. So you're using an asynchronous spiking chip in both cases, right?
Xylo is synchronous digital. Speck is asynchronous digital.
Okay.
I can talk about the reasons for that.
Yeah.
Speck is designed for vision processing, and it's designed to use event-based DVS-style visual input natively. DVS, event-based vision input, is fully asynchronous. It's a very sparse way of encoding a vision stream that has no clock associated with it. And sticking with that asynchronous nature of the input stream all the way through computation means we can make full use of that efficiency, that sparsity in the input stream. That means we can save energy for power consumption, energy for computation. No clock means we can save a lot of energy. Clocks are expensive. For Xylo, Xylo is designed for temporal signal processing tasks, which are usually continuous in time. And we also make use of a more complex neuron model, which uses temporal dynamics directly. And the easiest, cheapest way to implement that is to have a clock as part of that computation. The input stream for audio signals, for other input sensors into Xylo, are usually clocked anyway. And the temporal dynamics of the neuron mean that we need to have a clock there somewhere. We need real time. And so for that reason, we have a clocked synchronous digital design for Xylo.
That makes sense. So you also pointed out that the neural model in Xylo is more complex than in Speck. You said it's very, very lightweight in Speck, just a few adders and things. Can you talk a little bit about that?
That's correct. The neuron on Speck is probably the simplest possible digital spiking neuron you can come up with. It's simply a 16-bit digital adder and a 16-bit threshold. We have 8-bit weights. It's all digital integer logic. The only real complexity on Speck is the asynchronous digital nature of the computation. So we have single-bit binary events coming into a neuron. We have 8-bit weights associated with that input synapse. And the computation for the spiking neuron is simply adding that weight onto the 16-bit neuron state. Because we're operating event by event, and because each input event is a single binary bit, we don't even need to perform any multiplication with the weight. It's simply adding that weight onto the neuron state.
Now, on top of that, there is another layer of complexity in the sense that you're time multiplexing the neurons. So the neurons are not just doing their own job, they're acting for, I think you said, of the order of thousands or more. Can you talk a bit about that time multiplexing?
Mm-hmm. So it's a convolutional architecture, which means the weights are shared. And so we have to map a small set of weights onto a large number of neurons. And because we operate event by event, we only ever have to update a single neuron at a time, always. Because again, the simplicity of that digital neuron, a neuron state is simply a 16-bit memory value. So we have a very small processor unit which receives that input event, identifies which neuron and which weights are required to be updated, pulls those neuron states from memory, updates them, determines whether they should emit an event themselves, and writes those back to memory. So the neuron processor unit can be very, very small, extremely efficient, and then scaling up the number of neurons in a layer is almost as simple as just increasing the size of a small memory block, which is the state of each neuron.
We were talking earlier, and one of the things we were discussing is how much things have changed in neuromorphic engineering generally over the last few years. And that's partly because of deep learning and partly because we've managed to import the special sauce of deep learning into neuromorphic engineering, which is backpropagation and backpropagation in spiking networks. So can you explain a little bit about how that has looked from your point of view, that transition?
That's really been a game changer. In 2018, when the company started, when I joined the company, there weren't very good ways to build spiking neural network applications. In particular, backpropagation was not something which people were widely using for spiking neural networks. That has changed completely, It's now the main approach that we are using for building spiky neural network applications. And there are other software toolchains now available open source, which also enable that sort of approach. Backpropagation has been the killer app, I think, enabling deep neural networks in general, along with very cheap, large-scale computation and acceleration of that backpropagation approach. We make full use of all of the advances from the deep neural networks since 2010, of GPU-based acceleration and compute for training networks. We use backpropagation algorithms. We use the deep neural network built optimizers, for example, Atom, for optimizing networks. The big change since 2018 has been being able to apply these also to spiky neural networks and neuromorphic architectures. We now have off-the-shelf approaches embodied by our toolchains in SynSense for using backpropagation, using GPU-based training, using PyTorch and other machine learning frameworks to build spiky neural network applications. What it's looked like from the inside is starting from a feeling of needing to handcraft every spiky neural network application and needing to be a neuromorphic engineering PhD in order to do so, to where we are now in 2023, you can be a machine learning engineer, a deep neural network person who's never seen a spiky neural network before, has never touched neuromorphic hardware, and you can, within a few hours, build your first spiky neural network application and deploy this onto some neuromorphic hardware for inference.
And that's where Rockpool comes in, really. Now, you recently, as I recall, brought out some developer kits and unveiled Rockpool, which is your platform for allowing designers to create their neural networks and to train them. Can you explain what you're trying to achieve and how that works and what's different about it than some of the other things that we know about, like PyTorch and TensorFlow, maybe?
Rockpool is something we've been working on internally for quite some time, since the beginning of the company. Rockpool is a machine learning library for spiky neural networks. It's how we build applications for our technology, and it's how we deploy applications to our technology. It's designed to have a high-level interface very familiar to machine learning engineers. It looks very much like PyTorch. It looks very similar to Keras. These are standard machine learning frameworks used for non-spiking neural networks. It's designed to enable third-party developers who probably have never worked directly with spiky neural networks, but have some experience with machine learning with deep neural networks to build an application for our hardware very, very quickly and conveniently. Rockpool makes use of PyTorch and JAX, two automatic differentiation pipelines, as a backend to enable you to train a spiky neural network in a machine learning sense. So you can define your application by having a data set, by having a task, and then Rockpool will build a spiky neural network for you that executes that task and embodies that application.
The last question I'd like to ask you is about commercialization. You are a startup, you're a commercial company. So you are looking to the future and how you're going to grow your company. Do you want to talk a little bit about what you expect to see over, I don't know, the next 5-10 years of your development?
We take a very pragmatic approach to commercialization and to our existence as a company. Primarily, we are a commercial entity. We want to sell silicon. It just so happens that our hardware is neuromorphic, but that is secondary to the use cases and applications themselves. We need to find applications that we can do very, very well on, better than anything else. For that reason, Speck is going to be first cab off the rank in terms of commercialization. And the applications there are low-hanging fruit initially. Things like gesture interaction, presence detection. We're not going for what might look like very advanced research level applications. We're not going for applications where we have additional regulatory requirements, for example, automotive or medical type applications. We're going for consumer products, large scale volume, commercial markets. That's our focus. So this year is our first engineering sample sales year. We have several clients who are commercializing Speck for these sorts of applications. And we will take a similar approach also for Xylo, audio applications, motion applications. We start from what we can do well and what will be available, addressable at volume. These are the first easiest markets to commercialize. There are a lot of other very, very interesting use cases which we plan to commercialize in coming years. We're designing hardware for high resolution input and processing, which would be useful for external automotive applications, for example, autonomous driving. We're looking at other applications, for example, drone-based applications, indoor robotics, human movement for Xylo will come a little bit later. Motion control, these sorts of more advanced applications are things which we are starting to look at, but are not the easiest, simplest first step. And so for that reason, they come a year or two later.
What about learning? Do you ever see there being a time when you would want to put learning on your chips?
Coming back to what I said earlier about commercial viability and necessity for on-chip learning, where we do see a utility for that is in applications where you need to fine-tune the result for a consumer. So for example, audio processing applications, maybe a consumer would like to fine-tune this keyword spotting to their voice. That requires some degree of reconfiguration, but not necessarily on-chip learning. This can be taken care of off-chip. At the moment, in the next year or two, we don't see a deep need for on-chip learning.
Dylan Muir, thanks for coming on to Brains and Machines.
Thanks very much, Sunny. I appreciate it.
Hi, listeners. We recorded this interview in mid-2023, which is too long ago for us to want to put it out without checking on what had changed. So, in March, we called Dylan back to find out what's been happening recently. So Dylan, it's been a while since you and I last spoke, and lots of things have been going on at SynSense. Why don't you catch us up?
Yeah, thanks, Sunny. I think the biggest new development that we announced a couple of months ago is our acquisition of IniVation, the long-running DVS neuromorphic sensor company. This is a big deal for us. Obviously, we've been collaborating with IniVation for a very long time on Speck to build out our Speck system-on-chip smart vision sensor. We thought it made a lot of sense to work even more closely together with IniVation. This enables us to build alternative versions of Speck, different resolutions, different specifications. It lets us be a lot more flexible with how we can deploy and commercialize Speck. It also helps us address the Asian markets for DVS sensing much more effectively, using our distribution, our business development, bring DVS sensors into the Asian markets.
It was last summer that I interviewed you the first time. How has your strategy progressed since then?
I would say our strategy has broadened slightly. So in particular with respect to this acquisition of IniVation, we're now also looking at applications for neuromorphic sensing that might require a little bit of smart but more traditional compute. So expanded beyond strictly neuromorphic spiking neural network-based compute to what we always do, which is put a little bit of smarts as close to the sensor as possible, but allowing that to be maybe microcontroller-based or CPU-based, or even some custom digital circuitry, but still, nevertheless, very low power, close to the sensor as possible.
So is there anything else that you want to tell us about upcoming developments within the company or collaborations with others?
Nothing concrete yet that I can announce publicly, but keep your eyes peeled. I'm sure we'll have more announcements in the coming months.
Thanks for the update. We appreciate it.
Thanks, Sunny. I can't wait to discuss this interview with you. And for more about Dylan's work, please go to brainsandmachines.net. Now, we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University.
Hello, Giulia. Hello, Sunny. How are you guys doing?
Hi, Sunny. Hi, Ralph. I really loved the way that Dylan explained things as really calm and clear, but I kind of wanted more about him and about his research point of view. And I actually found out a paper that he wrote a while ago before SynSense about mice and the V1, so the visual cortex. And the paper is specific excitatory connectivity for feature integration in mouse primary visual cortex. So basically, they were showing to the mice overlapped gratings, and what they found is that neurons' response is not only simply predicted by responses to single gratings presented alone. It means that what we think usually is that we have neurons that are selected to a specific edge orientation. So what they are saying is that is not the case. So it's a combination of neurons that are responding to overlapped gratings. And this is so interesting. And this led me to think about the dispute that we have, for example, in attention, where we have in one case Treisman and Gelade that is saying that we perceive objects as a combination of features, so a combination of edges, and we integrate all of the things together. And the other approach, which is the Gestalt approach, where we perceive an object as an entire, let's say, system or entity. So I was actually wondering what Ralph think about it.
Yeah, so I'm definitely a Gestalt guy. I look at the entire object. I follow the argument that Pietro Perona at Caltech basically does, where he basically tracked eye movements and showed that we focus more on the central location of the object as opposed to the features of the object, right? Features meaning the edges or things of that sort. However, I do believe that it's a top-down and bottoms-up integration process, right? Bottoms-up comes from features. They come from the pieces that forms the object itself. Top-down is influenced by concepts, what a face is, what a car is, and so on. And those kinds of things come together and integrate and gives us a central location where it becomes the handle point, right? The point where you look at, and that's your attention is directed towards that. So in a way, I don't think there is any real debate that integration is important. The only thing is what exactly drives our attention might be a little bit different. We don't look at the edges, we look at the center.
Yes, as usual, is an integration of things and is a combination of different factors that works together. So now I would like to go to the juicy part, SynSense. I have a kind of a weakness for SynSense and specifically for Speck. It's a very cool device, right? Because we have the sensor that is integrated with the spiking convolutional neural network device, right? So that's very cool because it's integrated, compact, easy to use. If you want to do a simulation, it's a matter of half of a day and you have your simulation done. It's amazing. It's very easy to use. And this is really important because we need to think that there's not only us that want to approach to neuromorphic computing or spiking computing. There's even other people that maybe it's better if we put it in an easy way. And I think they are unique in this regard. Although you have other companies that has done some integration of devices like this. Do you know about neuromorphic devices combined together?
Sure. I mean, again, you go back to certain times, right? So in the 90s and the 2000s, there was a company by Tony Lewis called Iguana Robotics, where there's a combination of cameras and object recognition, right? They're all embedded within the same chip. There, though, the idea was a template matching scenario. It was not a learned inference in the classic way that we think about inference now, right? Where there is a neural network that's solving a inference problem. What Tony's sensor was doing was effectively getting a histogram distribution, if you will, of the object that it was looking at and then doing histogram matching, right? Which you could argue that's a kind of an early version of a neural net kind of scenario. And that was all on a single chip. Going forward, we have learned that we do not necessarily need to put everything on the same chip, right? So we basically started thinking, you can have the camera here and you can have this interface between them. And then you can have the processor that does the actual analysis. And the analysis can be of the form of neural network, can be of the form of classical CPUs, GPUs, or whatever the case may be, which is one of the approaches that he talks about in his system as well. So I think folks have been thinking about that. And just to kind of loop this all the way around, Tony recently, I believe, started with BrainChip. He's the CTO at BrainChip. And in fact, I think they announced a new product that they're selling that is some edge machine learning device that will, I imagine, take the kind of sensing data and then process it as well. But I don't think it's embedded. And what I mean by embedded is I don't think there's no cameras associated with the chip itself, right? It's more kind of a distributed system.
So now that IniVation, which makes these DVS cameras, and SynSense, which I apologize for calling Synapse all the way through this series whenever it came up in conversation. Now that they are one company, does that make them a threat to Prophecy? Certainly competition with Prophecy, which they've been throughout. And does it change anything? Does their approach make anything different between the two? I don't know from a commercial point of view well enough to make a comment.
Yeah, I guess I can speak to that a little bit, and then Giulia, maybe you can bring it in. So first, I want to say that I am a shareholder in Prophecy, full disclosure. So I think their IP, in a classical sense, is more on the camera side, right? And so it's more like IniVation in that sense. Whereas what seems to be like SynSense is more on the processing side of things, with the spike-based processing, the neural implementation, and so on. So in combining the two, combining a spike-based camera with spike-based processing, that gives them maybe an advantage in that sense. Whereas Prophecy is entirely on the imaging side.
I'm hoping to get an interview with Prophecy for the next season, when we'll also be talking to a lot more companies, including hopefully BrainChip, Rain Neuromorphic, and a few others. Sorry, Giulia.
Yeah, I just want to confirm what Ralph was saying, right? In the sense that the cool part, when I was a PhD student, we had two 80s cameras, so two Prophecy cameras mounted on iCub, which is the humanoid robot that we used in the Italian Institute of Technology. And connecting that to Spinnaker and trying to get the integration done, although those cameras are amazing, it's a pain. It's a pain anyway. So SynSense solved that integration problem. You have the spikes, and then you can process it with your spiking evolutionary neural network, and you do everything in one go. Which, from specific point of view of someone that wants to get things done, and it doesn't have 5 software engineers to ask for, it's easy to be done. So this is the thing that I loved the most when I started working with Speck and simulating with Speck. This is really interesting.
Have you used Rockpool?
I didn't use Rockpool, but I used Synapse and Tonic. But Tonic is to manipulate the events.
Do you know anyone who has? I'm just curious because it sounds like it would be an advantage to have this in-house PyTorch-like platform, but I'm not a programmer, so I wouldn't know.
I can speak for what I've done. For example, I was working on the attention model, and I was trying to understand how to make it run on the Speck, right? It took me half of a day to write the code for the attention, because you just need to load your kernel and that's it. It's done. And then you work with tensors. So it's very easy. So that's, I think, the best thing that you get from the Speck or from the SynSense idea, let's say, because I think the Xylo, it's done with the same idea, easy to use, which is very important. Maybe you can't get that crazy with connections as I used to do with Spinnaker, for example, but I got something done in half of a day, which is priceless. So that was really cool.
Absolutely.
So another point I would like to raise, which is kind of in contrast to what I've just said, but it's okay, let's go with the flow. So Dylan is saying that at some point he felt the need of encraft every spiking neural network application, and then you don't want a PhD to do that, right? So you want something easy. And then I fully understand the choice commercially, because they need to push this technology on the market. But then I have a question much more from the neuromorphic point of view, which I think that instead, at some point in the future, what we would like to have is specific circuits for specific application, or at least this is how I envision neuromorphic in the real future. What do you think, guys, about this?
Yeah, but I think we always thought that the road that some of these commercial entities were taking was the path of least resistance at this time, right? Given what we know, what we have, and what's available, what's quickly incorporated into different people's systems, the digital approach, which is what he's taken, the various approaches with different timing mechanisms, and whether spikes or not spikes and so on, all of that is to account for the fact that this is where we are. We need to make something that works now and have demonstrable applications. He's talking about just a detection, walking in and out of doors and things of that sort. But eventually, you could imagine, exactly as you said, Giulia, you would have a single tiny little micro-powered chip that would do everything that is being done on these digital platforms, right? As an old school neuromorph, I think that's ultimately the place to be. And when we get to smaller and smaller feature sizes of the nodes in which these systems are implemented, the voltage scale gets smaller and smaller. The gap between the spike representation and the level representation goes away, because you might only be able to do 2 levels when you're talking about half a volt power supply or something like that. So at that point, the specific circuits that you would develop and the more general purpose one that we use on a digital system might merge, and it might end up looking a lot more similar than we think.
I agree with Ralph in the sense that I think we're going to have the short-term wins and then hopefully eventually the long-term wins. It seems to me that in the short term, you need to just get people used to working with spiking networks and more unusual networks. And that once that kind of cultural transition has taken place, then the more custom tailored things, which, let's be honest, are going to be on the robots, are going to be on the really low-powered devices, maybe on the medical systems, biomedical implants, which will need a certain level of robustness maybe. And so you'll really want to design circuits that are absolutely perfectly implemented. I think that's going to be the second stage. So at the moment, it's just like with anything. You start off with a generic platform, which is just going to process stuff, whether it's, in this case, sound and vision are separate. But I'm sure it will become more custom as we go along.
Yeah, I don't want to spoil anything, but this is an important question that I asked Jens Petersen in the next episode. The problem that we're having at the moment is that we have too many softwares and hardwares and we don't know what goes with it. And having something that is easy to use, it's interesting and important because it's a good start point for anyone to try neuromorphic, in my opinion.
I think it's interesting because to me, it's just like computing just before I got involved with computing. So when Ralph and I were kids, there was the ZX81 and the Acorn, the Altair and all of these weird computers. And then there was just basically Mac and PC and Linux boxes through the 90s. And now pretty much everyone uses just a Mac or a PC. But you've got these different graphics engines and things that are being added to them. So I think you have to go through that period of diversity where people are seeing what works, and then you go through a period of everything's the same.
In fact, that's what I was going to say, and agreeing with you, Sunny. It's good to have that diversity right now. It's good to have all these different people thinking about the problem, and it will converge, right? It happens through acquisitions, it happens through demonstrations, but all these things converge. Eventually, there might be 2 or 3, hopefully more, but solutions that seem to be viable, and those are the ones that are developed even further.
And what you'll find is that some people will swear by different technologies. Individual applications, individual users will determine which of these platforms takes off. And of course, how much it costs, whether they have proactive licensing programs. There are all sorts of things. The other thing in technology is we all know that it's not always the best technology that wins, because there's no such thing as a level playing field, because business gets in the way of the science and which is actually the best technology. And all of us who are a certain age remember VHS and Betamax. And
I was thinking the same thing.
Well,
the other one was iPod and Zune. Yeah, it was Microsoft who made it for music. And they were much better than iPod, but iPod looked prettier, so iPod won.
Well, I think if you ever want to learn lessons about marketing, Apple is the place to go. Yeah. So, Giulia, what do you think? Can you see that there's room for diversity here?
So I was actually about to say, thanks, guys. I can talk to you, thanks a lot. Because from my perspective, from an early career postdoc perspective, it feels just, that's a mess. I don't know where to start, but it's so nice to speak with you guys because you calm me down somehow. And you are right, guys, because depending on what I want to do, I would choose to do it on Spinnaker, for example, which is old but gold, and you do lots of stuff. And if you want to do something else, I would do it maybe on Speck, or maybe I would try Luigi for other things. So I understand. Maybe I just need to embrace it, accept it as it is, and try to do it all.
I think we're actually quite lucky, Ralph and I, because I think we're a little bit too young to have been through the real cowboy days. So I think we understand your pain in the sense that we didn't quite have to go through that difficulty that people who maybe were 5-10 years ahead of us literally had to learn from scratch every time they had a new machine in front of them, right? But that's the way technology goes, is there has to be diversity before you have consolidation. And consolidation is interesting because we've already had consolidation between IniVation and SynSense, which is not surprising because they have the sort of same founders and are in the same city. I'm wondering how much of that is going to happen too within the coming years amongst the other Initerra and, we've got Prophecy doing these deals with Qualcomm. We've got BrainChip.
And I guess it's that, remind me of the name of the software tool that Dylan talked about. And
Rockpool.
Yeah, Rockpool. That might be their biggest contribution in the end, right? If that becomes the thing that makes it easy for all these different hardware systems to talk a common language, right? Who knows?
It could be, but these things tend to be transient. I mean, it was TensorFlow a few years ago, right? And every few years, there seems to be a new iteration of what everyone is using to program their networks. And with there being so much money in it now, which wasn't true 15 years ago, it will be interesting to see how these languages and software platforms kind of grow up around them.
Yep.
So Dylan had a very clear commercial perspective on why he wasn't going to add learning to his chips and why he didn't think that was going to be necessary anytime soon. Did you agree with his reasoning?
Not so much for me. I thought that online learning is important in the sense that, yes, you can start off your network knowing some very specific examples of what you're trying to detect, right? Be it gestures or be it keywords or whatever the case may be, right? But it would be good to, along the way, to be able to switch your network for a moment and say, oh, this is a new word or this is a new thing that I want to learn. And if you can switch over, learn that new thing without obviously forgetting what you've learned previously and then go back again to using it, I think that would be extremely useful. And also your voice and my voice and Giulia's voice are different, right? So how do we account for that and a new user and so on? So I think that form of adaptation and learning is still important in my view.
Yeah, from my perspective, I don't like it in the sense that I am exploring embodiment and adaptability of an agent moving into the environment. So from my research perspective, I don't see the not having an online chip learning as a feature, but maybe more as a bug, because it's basically probably most of the commercial application can be done with offline learning. And I think it's still a good idea to try to do something simple, see as it works, and then maybe make it even more complex later on. They're starting from scratch and they're making things easy, and then they can build on that. So I still agree with them.
It'll be interesting to see. I mean, I guess the argument could be that you don't need on-chip learning because you can do off-chip learning and just completely wipe the chip and reset it with the new weights whenever you want to, just as you would with a software upgrade, right? You're looking skeptical, Ralph.
Yeah, I mean, I guess you could do that. But the problem, I suppose, is encountering the right environment or the right data that upon which you are going to learn, right? In a way, I suppose if you have some mechanism for storing everything, for backing up all the examples that you encounter in the cloud and then going back and relearning it and re-uploading. So in a way, it takes away from one of the benefits of having everything localized, which is you're not connected to the cloud in any way. And that's the thing that you would lose out, I think, in that example that you articulate.
First thing that came into my mind, a drone in a warehouse. Once you've done object recognition of boxes or things that you know, that warehouse is going to have all of the time the same kind of boxes, right? So I think there's lots of applications that can be done still with their approach, but I agree that if it was more complex, it was better. But at the moment, I think that they can cover lots of applications still.
There's no question about that, I think, Giulia. I think they will cover a lot of applications, but it's the changes, right, that becomes a problem. So there's a leak in the roof where water comes and warps the boxes. Have they seen those examples of the boxes warped and being able to still think that they are boxes, not just paper, whatever the situation is, right?
Yeah.
So it's that kind of thing is, what happens when real world encroaches on the ideal scenario that you've learned.
Or if you recognize them as boxes still when they're wet, if you understand that the materials properties of these boxes are going to be completely different and they may collapse when you pick them up the same way you usually pick them up. Yeah, it's a good point, Ralph. I guess we will see.
Okay, that's a good place to stop. And thanks to Sunny for yet another interesting interview and Ralph for your insightful comments. Our next episode is a special one, in which Sunny and I will be talking to 4 young researchers, all of whom are making their careers in neuromorphic engineering. Kenneth Stewart, Fabrizio Tati, Jens Pedersen, and Laura Krine. We hope you join us then.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks to our guest, Dr. Dylan Muir. EE Times Current is available through the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find the transcript along with direct links to the other stories we've mentioned and other resources. Thanks for listening.